let's start with a few announcements. So Lab 7 will be due this Friday, and there's no lab this week other than turning in your lab this Friday. Exam 2 will be Wednesday, the 28th, during the class period. See the announcement that I sent out via Canvas. It has lots of details in there about the exam. You'll have the exam, the regular class period, plus the 30 minutes grace period, like we did last time. And so if you have any questions about the exam, stop by office hours right after this class on Zoom, and we'll talk about it then. And then my office hours, of course, are right after class, and the TAs are posted if you want to chat with them or work out any problems with them. And as always, ask any questions by unmuting or via chat. It's probably better to unmute because I miss the chat often. Otherwise, please stay muted so we can keep the background noise low. So I have up on the screen right now the decision tree for analyzing op-amp circuits. I went through this last time, and we did an example going down the left side of this tree, excuse me, but I wanted to bring this up so that I could show you. We use op-amps for two purposes: to create circuits that perform linear functions and to compare voltages. And so last time we talked about negative feedback and how that creates a linear op-amp circuit. And then we went to the left side of this tree and talked about the negative feedback approach. I'm going to work another problem like this today. And I mentioned that once you know the gain of, for example, an inverting and a non-inverting amplifier, then you could call that a common circuit. You never have to analyze it again other than to remember the gain. And if you don't remember the gain, you could always reanalyze it like we did last time. And then also during this class, we're going to go down the right side of this tree. So I'll talk about that in a minute. Okay. So the rules, and we're going to work another example problem today, are these. So you have an op-amp circuit. It has some connection between the output and the inverting input, and that means you have negative feedback. This cannot be through a power supply or a ground node. I'll show that in a little more detail when we get to comparators. And then you use this approach. You assume the input differential voltage is 0. You assume that the input currents to the op-amp are 0 into the inputs on the left. And that's because op-amps have high impedance inputs. It's not because there's anything special about an op-amp in a negative feedback circuit. It's just that op-amps have high impedance inputs, so the currents are approximately 0. And then you analyze the circuit using, well, whatever you have in your toolbox: KVL, KCL, Ohm's law, voltage division, for example. Okay, so let's work an example. And I'll bring my whiteboard up here. Okay. So I'm going to draw out a circuit that is a little more complicated than the circuit we worked on the two circuits we worked on last time. We had 2 resistors and an op-amp in each one of those circuits. We solved both of those by writing one KCL equation at the inverting input. And so let's make a little more complicated circuit here. So let me draw this out. So I'll draw this out instead of having this kind of pre-prepared. I want to give you time to draw this out if you're doing it yourself in your notes. So I'm throwing everything into this problem right here, trying to put a current source, a voltage source, couple voltage sources. Okay, so something like this, and we want to find VO, the output voltage, and IX. Okay. So I've defined VO as an output voltage kind of arbitrarily. Let's say that this 1 k ohm resistor is a load resistor, right? So it's just a resistor you connect to the output of this circuit. And this circuit is doing something. I don't have an input drawn here, but maybe the input is like the current into the left side of the circuit. And it's pretty much an academic circuit, especially with this voltage source in the feedback loop here. But let's go down the decision tree. So we have an op-amp circuit because it has an op-amp. By the way, I don't show any power supply connections on this op-amp, which means I'm assuming it's sufficiently powered. So it doesn't really matter for this circuit what the voltages are. You're just assuming that it's sufficiently powered by power supplies. I observe a connection between the output and the inverting input. The inverting input's the one with the negative sign next to it. So we have negative feedback, okay? That's how you identify negative feedback. If you can take your pen and you can trace through a path that gets, or along a path that gets back from the output back to the inverting input, then you have negative feedback. Now, remember I said, unless it's, you can't have negative feedback through a node that's held at a voltage by like a voltage source or a ground. This power supply here, this source is not that. This source just enforces a potential difference between both sides of it. If one side of this power supply were connected to ground, and again, I'll show you a better example of this, but then you could not have a feedback path. And so let's hold off on that. I'll show you an example of where you don't have negative feedback in a comparator. But here you have negative feedback. So we've established that. Okay, so what's that mean? That means that we have, well, first we can assume that VID equals 0, right? So we have 0 volts between the inputs of the op-amp because of negative feedback. And because the op-amp has high impedance inputs, I can assume there's 0 amps going into that op-amp, okay? So I think that's step 2. Step 3 is analyze the circuit using KVL, KCL, Ohm's law, whatever you have. Okay, so let's do this. So when you're looking at this problem, you have problems like this in your homework. And what I like to do first is just start observing what's happening in the circuit before writing any equations. Okay, here's what I mean by that. Let's look at the left side of the circuit. I have 0 amps going into the op-amp, right, out of this node here. I have 5 milliamps coming into this node from this source. And so I know that I have, it's like a mental KCL equation. I have 5 milliamps going that way, right? 5 milliamps coming into this node, nothing going into the op-amp. So 5 milliamps must continue through that feedback branch. Again, just without writing any equations, I'm observing this. I have 5 milliamps going through a resistor. So, you know, by now you can guess that's going to be 5 milliamps times 2 k ohms. Well, not guess, you know, 5 milliamps times 2 k ohms for the voltage across this resistor with that polarity. So you have 10 volts across that resistor. okay, by Ohm's law. Okay, so also I can observe that I have 5 milliamps coming down this way. Might use that later, just kind of writing in what I know on the circuit, right? 5 milliamps goes through this branch, comes down that way. Okay, the voltage I'm looking for is VO, and VO is a node voltage, and that's the voltage between this right node and ground. So that's explicitly what VO is, okay? So I think we have enough now to write an equation to find VO. Why do I say that? Because I'm imagining, well, first let me point this out. When you have multiple grounds in a circuit, you can assume that all those grounds are held at the same potential. And the way to do that is to connect them together, right? They're all 0 volts and they have to be held there. So I'm going to actually draw a wire. If you want to, you can do this. You don't have to, but I'm going to draw this wire connecting all the grounds together. Just like when you're in lab, right? If you have a bunch of grounds, you have to connect them all together. So this is what that's doing. And I can use that ground as part of a Kirchhoff's voltage law loop. And so I want some loop that has VO in that loop, and then other known voltages. Well, if I come here, let's see, go this way, go up through this source, I know that voltage. I know 0 volts across the inputs, right? 10 volts across that resistor. I have that voltage across that source, and I'm back to my starting point. So let's try that. Let's do that. So I'm gonna like write in this loop here. I'm gonna go this way, right? Go like that. So that's my loop along that green path, if it looks green on your screen. So that is a KVL equation that I'm going to write. So let's do that. Plus VO, right? Minus 3 plus 0, right? I'm going from here to here. That's plus 0. Plus 10 plus a negative 4 equals 0. I'm back to the starting point. Okay, and so if I do this right, let's see, I have 10 minus 4 is 6, minus 3 is 3. I think I have VO equals negative 3 volts. Okay, so I've just solved for VO. Are there any questions on that? How I either got any of these kind of fill-in voltages and currents, or how I wrote this KVL, or anything about that? Oh, okay. Someone asked, what if I had gone through the 5 milliamp source? Well, here's the thing. Without knowing anything about the circuit, I could tell you what the voltage is across the 5 milliamp source now, but I don't know. Right offhand, I don't know what the voltage is across that source. Without looking at the rest of the circuit, I don't know what that voltage is across that source. A current source is going to have whatever voltage it needs across it in order to cause the current to flow. Just like a voltage source can have any current through it to make a voltage happen, a current source can have any voltage across it. Well, you know, I know now that if I have 3 volts node voltage, let's say right here at the top of the source, then I have 3 volts node voltage at this node up here. So I know this is 3 volts. Like I could do a KCL equation. But before I started the analysis, I didn't know that was 3 volts. I can figure that out later. Okay.
Question.
Okay. Oh, go ahead.
Couldn't you have just taken a loop through the 3 volts and then follow the wire down through V0?
You mean across the op amp?
Yeah.
Actually, you cannot do that because there's a voltage here between here and here that you don't know. In fact, if I did that, the answer I'd get is positive 3 volts, not negative 3 volts, right? Because a minus 3, let's pretend that's 0 volts, you get positive 3. So yeah, what I recommend is at first, I mean, you can figure these voltages out later between input and output of the op amp. but at first you don't know them. So your loop should not involve going from input to the output of the op amp.
Got it.
Okay.
So
Okay.
just
So go ahead.
yeah, so Professor, kind of in line with that, when we're sort of picturing this loop that we're creating, is there some kind of path that goes from the like positive input voltage to the negative input voltage within the op amp?
You mean, do you mean is there a path from the supplies or from the inputs?
Um, no,
Ju-
from the inputs. Yeah. So is there like is because I thought that KVL you use it along a path within the circuit. So
Yeah.
then if we're going sort of across that zero voltage, is there some kind of path connecting the positive input and the negative?
Mm-hmm. Yeah, in my KVL, I had to put this +0. That +0 is going from this node to this node, right? So whenever you go, I'll say across a component or across, from one node to another, you have to account for that voltage in your KVL equation. So right, I said -3, and then as I go from this terminal to this terminal, right, I know I have 0 volts across there. So I am adding a voltage in there when I do
Oh,
that.
gotcha. All right,
Mm-hmm.
thank you.
All right, someone said, could I reiterate the assumptions regarding the op amp? So the assumptions in a circuit with negative feedback, okay, only in a circuit with negative feedback, you're going to make the assumption that the input differential voltage, that's the voltage between the inputs, is approximately 0, okay? And that the current into the op amp inputs, both of them, are approximately 0. And then you analyze the circuit. Let me address, is it really 0, right? Is it really 0? Let's suppose that for this op amp, remember V out, right? The V out of the op amp equals AOL times VID, or V1 minus V2, right? This is VID between the inputs. And what I'm telling you, how could this be? If VID is 0, exactly 0, and let's say AOL is 10 to the 6th, that's some big number, 10 to the 6th. If VID is 0, then the output is 0, so that can't be right. So what is the voltage VID? Well, I could figure that out. Assume this is right. You can measure the circuit, build it and measure it, and it'll be right. But let's assume that's right. Let's figure out what VID really is, not the assumed value. It's going to be V out over AOL, which is equal to -3 divided by 1,000,000, right? Which is -3 microvolts, right? That's small. That's 0. I want to see if I can do this. 1, 2, 3, 4, 5, 6 volts. Compared to the other voltages in the circuit, right? -3 volts here, 4 volts here, 10 volts here, 3 volts here, right? Compared to the other voltages, this would fall off as, you'd round that off. So that's why I say, even if you take it to 3 digits, or 4 digits, you're going to chop that off and call it 0. So because AOL is so big, that's why you can assume the input differential voltage goes to approximately 0. Okay. All right. So what we've figured out now is VO. Now we want to figure out IX. Let me get rid of this here. So IX is the current coming out of the op amp. And I think I can figure that out because I have -3 volts as VO. We figured that out. Which means, if I can write it in a different color here, which means with -3 volts, I have 3 milliamps coming that way, or alternatively, right, I have -3 milliamps going the other way, either way. Okay, so I have 5 milliamps coming down from the feedback branch. I have 3 milliamps coming up from ground, right, because that's a negative voltage. So into this node. So that means I have, right, a sort of a mental KCL equation. I have 8 milliamps going that way. If you really want to write, if we want to be strict here, we could say KCL, let's sum the currents leaving that node. Not sum the currents entering that node. Sum the currents entering that node. IX plus 3, right? Plus 5 milliamps equals 0. So again, IX equals -8 milliamps. Okay, because you have -8 milliamps going that way. So that's typical of an op-amp problem with negative feedback. You're given resistor values and source values. If you have negative feedback, you make the assumption at the inputs, 0 volts, 0 amps, and then do what you need to do with KVL, KCL, Ohm's law, in order to solve whatever the problem is asking for. Okay. Here's a question. Right? People ask me, well, wait a minute, you have 0 milliamps coming into the op-amp from the left, and you have 8 milliamps coming into the op-amp from the right. Where's that going? Well, here's where it's going. So if I say plus, minus, and I'm going to put a ground there, if you can see that. This is VCC. It's some voltage, like 10 volts. And I'm going to put another voltage source here, plus, minus, again to ground. Maybe, so this is VEE. That could be something like minus 10 volts or something. So this current coming into the op-amp, in this case, is going down to VEE, right? So this is a negative voltage. This is something like, I don't know, negative 10 volts, and this might be positive 10 volts here. And that's where that current is going. If you had 8 milliamps, let's say, coming out of the op-amp, you'd have current coming from VCC, from that source, down into the op-amp. I showed you all those transistors in there, going through those transistors, and then coming out of the output of the op-amp. So that's where that current either goes into, that's called sinking a current, or comes out of, that's called sourcing a current, right? So, okay. Any other questions about this problem? We'll move on to comparators. Okay, let's get going on to comparators then. Okay, so in order to talk about comparators and how they work, we're going to talk about the limitations of op-amps, their limits, what they can't do, or a point beyond which they can't do something. And that's important because we're actually going to use one of these limitations as a feature of an op-amp. How's that for marketing? We're going to take this deficiency and make it into a feature that we're going to implement for a useful purpose, like a thermostat. Okay. One limitation of an op-amp is called the output voltage swing. And that means this: the output voltage of an op-amp must be between its power supply voltages. In other words, the output can't go higher than its positive supply voltage. It can't go lower than its negative supply voltage. Kind of intuitive. If I have 10 volts at VCC and maybe minus 10 volts at VEE, then the output has to fall somewhere between those two voltages, right? So here's the output voltage swing here. Stated in an equation, V out is between VEE and VCC. Okay. There's usually some margin between the output voltage and VEE and VCC. In other words, if I have, I mentioned minus 10 volts for VEE and plus 10 volts for VCC. If I have a really cheap, low-cost op-amp, old op-amp, I might only be able to get maybe within a volt of VCC. So maybe I can only go up to 9 volts with V out, maybe only down to -9 volts. For more expensive, more sophisticated op amps, you can get almost to the voltage rails, they're called, right? These are voltage rails because you're bound between those rails. You can get really close. They're called rail-to-rail op amps, maybe within millivolts. Okay. And I mentioned we're going to use this limitation. This is the limitation we're going to use as a feature to create a circuit that compares two voltages, the comparator. If you break open the data sheet, you'll find this table for the 324 op amp. I think this is the one you have in your kit. It shows you this. If you have, your high output voltage, let's suppose you have a 30 volt supply on VCC. Then depending upon the load resistor you have connected, for the LM324, you're going to get somewhere typical 28 volts, right? With a 10K ohm resistor, you're going to get 28 volts maximum. Even though you have a 30 volt supply, 28 volts maximum. In the case where you put a smaller resistor and you're drawing more current from the op amp, you're sourcing more current, then you can only get 26 volts. So there's some margin there. This is a really cheap op amp. It's good, it's useful, but if you have to get close to the voltage rails at the output, this is not the op amp for you. And then you'll see here, let's see, they talk about the low voltage. So what's the low voltage you get out if let's say VEE is 0 volts? You can actually get down into the millivolt range if the output is meant to go low and VEE is 0 volts. Okay, so that's just an example. But so just remember this. We'll use this as a feature shortly. Let's talk about another limitation that practically affects the circuits we've already talked about. So this limitation is called the output current limit. And this simply is the currents out of and into an op amp's output. Remember, current can come out of an op amp output and current can go into an op amp output, as we saw. But this current is limited to some maximum value. Okay, drawing this on the symbol, this is what it looks like. So, you may have some big circuit around this op amp, but the current I out is limited to a maximum value. So for positive I out, right, I out is less than or equal to some value, right? So it might be 10 milliamps. For negative I out, right, the absolute value is less than some sink value. So the op amp can source some current maximum. The op amp can sink or take in some current maximum, and there's a limit to that. The important thing to note here is that if you have a feedback path, and you will have one in lab when you do your lab circuit, but if you have a feedback path, that feedback path takes some current. So you may be trying to, let's say, have that current flow out of your circuit, maybe to turn on an LED or a light or something like that. That's not the only current that this op amp has to source. It also has to source current down into the feedback path, maybe to make something happen as a linear amplifier. Okay, so keep that in mind. And by the way, this is why, remember I said the gain of an inverting and non-inverting amplifier only depends on the resistors that you use. I'm sorry, the ratio of the resistors that you use, right? We had that gain expression. And it was just a ratio of resistors. It didn't say like, can I use 10K ohms and 1K ohm? Or can I use 10 ohms and 1 ohm? Well, you'll find, and again, we'll cover this later in lab, but you'll find if you use in the K ohm range, you'll have like, milliamps in your feedback path. If you use ohms, your feedback path would try to have amps, right? You don't want to do that because these op amps can only have maybe a few milliamps, maybe up to like 50 or 100 milliamps coming out. So if you try to have an amp go through your feedback path, it's not going to work. We'll cover more on that in lab. But I wanted to put this into context, why we care about this. Here is a table out of the data sheet. So this op amp can support up to 10 to 20 milliamps, right? Typically 20 milliamps out of its output. It can sink or take in to its output 8 milliamps. So those are different values. Okay, so kind of the takeaways here: consider the current required by the load connected to the output of the op amp, and also consider the current through the feedback path when designing an op amp circuit. Okay. So we've covered voltage limits, we've covered current limits. Let's talk about speed limits, reaction time limits. An op amp speed is characterized by slew rate. So this is another limitation. The rate of change of the output voltage is limited to some maximum value. So not only is the voltage itself limited, but the rate at which it changes, and like volts per second, right, how fast it changes, is limited to a maximum value. That maximum value, oh, let's see here. My computer just locked up on me. There it is. The maximum value that the output voltage can change is called the slew rate, specified in, as I mentioned, volts per second, more commonly in volts per microsecond. It's usually that big of a value that you specify it in volts per microsecond. So if you have an op amp and you have some output voltage that is a function of time, changes with time, then this defines the limitation. The derivative of the output voltage, in other words, its slope, its change per time, is limited to the slew rate, either in the positive direction or negative direction. So what's this mean? This means if you were to make a plot of V out versus time, then at every point in time, you could have a maximum slope. So right at 0, if I have a voltage at 0 times 0 volts, I could have a voltage that maybe increases like my mouse is going, right, over time, but I could not have a voltage that increases like my mouse is going over time. That would exceed the slew rate. So if I tried that, if I tried to have a voltage go up like this, right, what would happen is the op amp would clip it. It would distort the signal, and it would follow the slew rate line here if I tried to increase faster. This happens at every point in time. So you got to imagine that limitation applying at any voltage and time period, time point in the output voltage. You can find this again in the data sheet. Here's the LM324 slew rate. So 0.5 volts per microsecond is the slew rate. That means 500,000 volts per second, right? 0.5 volts per microsecond. That means that, not that you're going to change by 500,000 volts, but when you go from 1 volt to 2 volts, that's the maximum slope you could have, is 0.5 volts per microsecond.
Professor?
Okay. Yeah.
So is V out always time dependent? Because I thought from what we've seen that it was constant, but.
Right. So, well, imagine that inverting amplifier, right? I drew a sine wave for the output. So if you have, let's say, an inverting amplifier that multiplies the input voltage by 10, I could have a 1 volt sine wave amplitude at the input, and that would be a 10 volt sinusoidal output. Does that make sense?
Can you say that again?
Oh yeah, sure. So in fact, let me go to my board right here. So if I have, I'm going to draw, I can draw an inverting amplifier really quickly. So this is V in, this is V out. Okay, so I think what you're asking is have we always worked with DC values at V in and V out?
Yes, that was what I was wondering about.
Yeah, so what you could have is you could have something like, let's say this is 5K ohms and this is 1K ohm, and so what this is an amplifier with a gain of -5. So if I have something like 2 cos omega t at the input, this volts, right, applied here with some source, then at the output, what I would see is 2 volts times -5, so minus 10 cos omega t, right? So this cosine, you know, well, that's not cosine, that's a cosine. The cosine does that versus time. I could not have the slope of this voltage, right? Here's a slope right here. I can't have the slope at that point exceed the slew rate, or else that output is going to get distorted.
Oh, okay, I see. All right, thank you.
Yeah. And you can imagine, I don't have a slide on this, but you could imagine that cosine has a maximum slope. In fact, its maximum slope happens at the zero crossing. So the slew rate implies that there's some maximum frequency that you can operate an op-amp at. Okay. So if you're trying to amplify audio signals up to maybe 10 kilohertz, 15 kilohertz, then you got to choose an op-amp with a high enough slew rate. Okay. Other questions on any of those limitations?
Oh, Professor?
Yeah.
So this is going back to output voltage swing. How was it again that you could have a V out really close to VEE or VCC?
If you have a more sophisticated, more expensive, higher capability op-amp that allows that.
Okay.
Yeah, some of those use, instead of bipolar junction transistors, they use field effect transistors, and some of them use both NPN and PNP transistors that will allow you to get closer to the rails, the power supply voltages. We're not going to get into that, but you could find in the data sheet when you're looking for an op-amp how close it can get to its power supply voltages.
Got it. Thank you.
Mm-hmm. Okay, so this leads us into comparators. Comparators compare two voltages. And so I brought you down the decision tree earlier, and we went down the left side. We're going to go down the right side of this tree now. So these circuits, the comparator circuits, do not have negative feedback. Okay. And so in this class, when you see a circuit that does not, it has an op amp and it does not have negative feedback, it's going to be a comparator. So a simple comparator, I'll show you, it's one type of comparator, and then there's a comparator with hysteresis. And again, we'll cover these. Let's go down this right-hand side of the tree. So a comparator compares two voltages. And roughly described, what does this mean? This means that the output of the circuit is going to be high if an input voltage exceeds a threshold voltage, and it's going to be low if the opposite is true. Or alternatively, you can do this. You can say the output voltage is going to be high if the input voltage falls below a threshold voltage. I can build that also. And it's going to be low if the opposite is true. So you're comparing two voltages, and the output is either going to be high or low, and that's an indication of which voltage is higher than the other. Okay, so this allows an electronic circuit to compare voltages and make decisions. They're very simple decisions, but they're decisions. For example, should the circuit turn on a heater or not turn on a heater? And that's a thermostat. So comparators are used in thermostats. Okay, so I'm going to bring you back to the whiteboard. I'm going to talk about comparators and the theory behind them. try that again. Okay. So if I have an op amp, let's just talk about the op amp alone, and I'll put some power supply voltages on this also. Okay, and let's actually make VEE equal to 0 volts, or I'm going to ground VEE, and let's make VCC 5 volts. So there's some voltage source that's 5 volts connected between this top node and ground. And so, and V1 and V2 are the input voltages as shown. So you know that V out, as we talked about, is equal to some big gain times V1 minus V2, as long as you're within the limits of the power supplies, right, the output voltage swing limit. Let's take an easy number for AOL. Just let's make it 10 to the 6th. That's a pretty big AOL, but let's use that. And what I'm going to show you is how this circuit, just as it is, makes a decision on whether V1 is greater than or less than V2. Okay, just as it is. I'm going to build a table here, V1, V2, V out. So here's my table. And let's choose a couple voltages. Let me say I apply 4 volts to V1, the terminal V1, right, the non-inverting input, and I apply 3 volts to the inverting input. Okay. So this equation over here for V out says, well, V out, right, I don't have negative feedback. There's no negative feedback, so I'm going to fall back on what I know about an op amp, that V out equals AOL times V1 minus V2. Well, 1,000,000 times V1 minus V2 is 1 times, it's 1 volt times 10 to the 6th. That's 1,000,000 volts. So this op amp is going to have 1,000,000 volts at its output. Well, actually not. Remember, the output voltage swing says the output voltage is going to be limited to a voltage between VCC and VEE. Okay, so let's assume this is a good op amp. I'll show you another way to do this, so we're not going to get 1,000,000 volts at the output. We're going to get the biggest positive voltage that's possible at the output, which is approximately 5 volts. Okay. Because of output voltage swing, it's not going to go to 1,000,000. Okay, let's change V1 to 2 volts. So I change my power supply attached to V1, make it 2 volts. Let's keep V2 equal to 3 volts. So let's see, 2 volts minus 3 volts is -1 times 1,000,000 is -1,000,000 volts. Well, again, we know that's not going to happen. We're not going to have -1,000,000 volts. We're going to have the lowest voltage possible out of the op amp, which is approximately VEE, which is 0 volts. Okay. So we've built a circuit here that when V1 is greater than V2 by any appreciable amount, right, by anything greater than a few microvolts. So when V1 is greater than V2, the output is going to be high. It's going to be the high voltage. We're defining that to be 5 volts. When V1 is less than V2, then we get this characteristic that the output is low. Okay, so this op amp is sensing the voltages and making a decision which is higher than the other. Okay, so I could do this. I could create a useful circuit. Let's draw that out. If I have a temperature sensor, and let's suppose that output voltage, is some voltage, and I'm going to say that's proportional to the temperature. Right, so it's some voltage, it goes up with higher temperature, it goes down with lower temperature. You can buy those. And then I have a comparator circuit. Or a circuit that has a comparator in it. And it outputs a voltage. I'm going to call that the output voltage. And let me call this voltage on the left the input voltage to the comparator. And then I could have some kind of heater controller or heater. Right, this comparator can't directly power the heater, but it could power a transistor that turns on the heater, or a relay. So what I want is at some given threshold, right? Threshold. That's the temperature you want to hold with the heater. You're going to compare the threshold to the input voltage and decide whether to turn the heater on or not. So that's what you can do with something like this. Let's draw that characteristic of what we want here. Like what we want the output voltage to be given an input voltage. Okay, so let's suppose we have some temperature where we want to hold the house, the apartment, whatever, right? And we're going to call that the threshold voltage or the reference voltage, Vref. There's a data sheet. Oh, you can't see that. That says Vref. So that's proportional maybe to the temperature where you want to hold the house. So what you want is, let's suppose, right, V in is proportional. I'm going to say proportional to temperature. And so at low temperatures, you want the heater on. So you want the controller voltage to be high, the output of the comparator to be high. And then as soon as the house heats up and maybe the sun heats it up some more, you want the output to be low. So this is the kind of characteristic that you want for this comparator that is taking the input from something like a temperature sensor and outputting a control voltage to turn, let's say, a heater on. If I were to write this out, kind of this characteristic that we want here, it's V out equals VCC, right? It equals VCC when V1 is, well, actually, this is the opposite. We want to do the opposite here. Let's see. We want the output to be high when V in is less than Vref. And we want the output to be low, right, VEE, when V in is greater than Vref. Okay, so we're going to equate next time. We're going to say, okay, great. I have this reference voltage. I want to apply the reference voltage to one of these inputs. I want to apply the input voltage to, well, another one of those inputs, the other input, and I want to make this characteristic happen so that I could build a thermostat. Okay. All right, so I think that's all I want to cover today. We only have a few seconds left, 10 seconds left. So in closing, don't forget Lab 7 is due this Friday, but there's no homework this week. There's no pre-lab due this week, no quiz this week. Just concentrate on the exam, which is Wednesday. Take a look at the announcement I sent out on Canvas. It gives some details on the material covered and also the time period of the exam. Thanks for joining class. I hope it's working out well. If anything isn't, please let me know. And I will start office hours in about a minute, and we'll start out with talking about any questions about the exam. So if I don't see you in office hours, I will see you next time. Have a good night.